Welcome to another topic of statics. I would like to dedicate today's lecture to a simplification of force and couple systems for some of the more complicated structures and scenarios that we encounter in statics. So our objectives simply there two: determine the effects of moving a force, and B, find an equivalent force coupled system for a system of forces and couples. As such, certain activities that we would perform today is a reading quiz, applications, equivalent systems, system reductions, a concept quiz, a group problem solving, and attention quiz to wrap it up. So let's take a look at a reading quiz, a general system of forces and couple moments acting on a rigid body can be reduced to a single force, single moment, a single force and two moments, single force and a single moment. This question is a little tricky. It can be theoretically a general system can be reduced to a force and a single moment, but it could also be reduced to a single force and two moments. C and D are both correct, but the correct answer here is D. A more correct answer would be D. Number two, the original force and couple system and an equivalent force couple system have the same Planck effect on a body. Again, if we have the original force and couple system and an equivalent force couple system, and they should have the same external effect on a body, otherwise we really cannot call them equivalent if it has a different effect on a body. Some applications that we can think of here is the resultant effects on the person's hand for these different scenarios, depending on how the person is actually holding it. Is he moving the hands with the applied force and so on? And the reason for that is because the condition of the supports in any structure greatly affect the reactions, the external forces, and that will be developed as a result. If his hand here in this case, so for example, is free to move, there will be no moment being induced at the end of where he holds his hands, but by the same token, if it is fixed, then there would be a moment at the end of that particular beam caused by the condition of the support. In more advanced topics, we're actually talking about degrees of freedom of different structures, but that's beyond the scope of this course. So more applications are also given here. For example, the case up here, there are several forces and a couple moment acting on this vertical section of an I-beam. This is could be considered a column, could be a beam. In this case, assumed to be a beam. But as you can see, it's pretty complicated. There are three forces, F1, F2, acting on that, and there's also a moment of 500 Newton meter acting on the structure. It makes it pretty complicated. It's impossible for us to reduce this entire system. If you want to design this beam, then can we reduce that into one moment as shown down here and a force? That is possible theoretically speaking, and we want to make sure that we understand all the external effects and also make sure we don't follow any conditions of equilibrium and any of the static laws, but that is possible. So when a number of forces and a couple moments are acting on a body, it is much easier to understand their overall effect if we can combine them into a much simpler form, maybe a force and a body. Now that is possible by finding an equivalent system that have the same effect on the body itself. So let me just take you to this slide. Also moving a force on its line of action. In this case, the force F is acting along the line AB, as you can see here. Okay, and we would like to pretty much take a look at different vectors, line of actions in this case, and show that the vector's line of action does not really change the external effects. So that's important to realize. The second thing is if we can find a vector called a sliding vector, like a slide, then that would be what we call a replacement to that force vector. We call it the sliding vector. So obviously, as I've shown you already, when we move this force along the line of action, or if we change the condition of the subforce, there'll be a change in its external effect. We want to make sure that those external effects, they remain the same if we can find a couple moment, what we call the free vector we have so far along with the line of the couple, so we can apply it at any point on this body, but cause the same, cause an equivalent external effects. So how can we achieve that? Well, we can achieve that as long as we can pretty much sum all the forces up, and we can sum all the moments up. The system that is shown here, again, the very first one on top is pretty complicated. Then we take the summation of the forces. If we can pretty much apply them to one point, of course, when we do that, then we need to take care of the external moments that is caused as a result of moving a load from one point to another. For example, if you continue F1 here, obviously there would be a moment due to moving the F1 from here, the red place, the red arrow to F1. So if we want to bring that from the current position to the red arrow position, of course we need to consider the effect of the moment that is associated with that, and vice versa. We can also, after bringing all the forces into one point and all the moments going through the same point, then we can simply replace the entire moments and the forces with one single force and one moment, force couple moment. So we need to, of course, follow all the rules that are associated with that. Let's take a look at the force system that lies here within the XY plane. It's a 2D case. The reduced equivalent system can be obtained using the following three scalar equations. Okay, so as you can see, this is a simple case of a red light pole, or the transportation light poles. There are two lights. One is at point W1, one is at point W2, acting downward. We express them as W1 and W2. They're a distance away from the point O. It is extremely important to design such a pole properly. make sure we consider the effects of the moments and external moments and the effects of other external forces. So W sub R, which is the resultant force acting on the pole, would be W sub R plus the moment, assuming that this point O is a rigid connection. It's important to also realize that M sub R sub O would also be created as a result of W1 multiplied by D1 plus W2 multiplied by D2. So we can replace such a system with a force moment system. So if, in this case, for example, F sub R and M sub RO, as shown here, are perpendicular to each other, then the system can be further reduced to a single force F sub R by simply moving F sub R from point O to P. So in these three cases, these are three special cases. They are coplanar, they are concurrent, and they are parallel. The case of the parallel is this first one. Okay. In this case, you get parallel forces. The second one is they're acting in the same plane, and also the case of the concurrent forces that are shown in here. Let's take a look at an example to see how we can achieve something like that. In this particular example, a 2D force system with the geometry as shown is given. We would like to find the equivalent resultant force and couple moment acting at A, and then the equivalent single force location measured from A. Okay, and so make sure to understand what we are actually looking for. We are trying to find an equivalent force. This forces acting on this system, they're going to result in a moment and also in forces, the reaction of the forces at point A. We would like to see if we can find an equivalent resultant force and a couple moment acting at A, and then the equivalent single force location measured from A. Let's see if that is possible. Okay, so let's try to see what plans should we develop here. We would sum all the X and Y components of the forces to find F sub RA. Okay, so we call it F sub RA because that's the F sub reaction at A. These discussions, they eventually lead us to have a good understanding of how we can calculate the reactions and how we can actually replace a more complicated system with a much simpler system for simplification purposes and to reduce the computational costs. So we find and sum all the moment resulting from moving each force component to A, and we would shift F sub RA to a distance D such that when we divide that M sub RA moment at the reactive moment at A divided by the force, it would provide us the appropriate distance. So the first thing we do is we take the summation of forces in the X direction, we set that to 0. We take the summation of forces in the Y direction, we set that to 0. Again, if you want to do the X and Y component of each force, this is the X and Y component. For this force, the same thing. We would actually use the X and Y component of the forces. Then we would actually take the summation of those. Okay. Again, this one is the 150 times 3/5, and that will be the X component. Okay. This is the X. For this other one, this is the X. This is the Y component, and so on. It's supposed to be Y. Okay. So in this case, we can take 3/5 and we take the 4/5 of the triangles as they're shown here, 3, 4, 5, and this is also a 3, 4, 5 triangle. Then we use the same procedure to calculate the summation of forces in the y direction. So that would be 180. Note that we didn't set this to 0. We're just summing them up. Then the summation of moment about A is also calculated, because as you can see, this force doesn't contribute to any moment about A. It's this component of the 150-pound force doesn't contribute to that either. So we end up with 3 components. One is the X and Y component of the 100-pound force, and they are considered here. The distance for one is 1 feet, the other one is 6 feet, and also the 100 and the Y component of this 150-pound force that's shown here, and this is the Y component. That would also cause the moment. Multiply that by the moment arm, which is 3. We consider the directions. Again, in this case, we assume clockwise is plus. Again, as I mentioned, it doesn't really matter which direction, as long as we stay consistent and we apply it to all of the forces that are associated within one system. In this case, minus 640 pound-foot would be the moments. Now, where should that moment be applied, and what should be the angle in which it applied? In this case, we take the so now we're gonna take the squares of each component. There's a 60 pound, we square that, and we add it to the square of 180, and we take the square of that, and so the force would be 190 pounds, and the angle simply would be 180 divided by 60. Again, the reason for that is the Y component is 180. We just take the ratios, and that would be 71.6 degree. So if you want to find the equivalent single force F sub R, it can be located at a distance D measured from A. Again, 640 divided by 180 is 3.56 feet. Okay, let's take a look at the second example. In this case, there's a slab that's subjected to 3 parallel forces. The equivalent resultant force and couple moment at the origin O is what we are after, and we also would like to find the location of the single equivalent resultant force. Again, we would find the F sub RO, we would find the M sub RO, and we pretty much, in order to find the location of a single equivalent resultant force, we would use the X, the location of the force, the X component and Y component as such, or this is simply the coordinate of the point itself, and the X coordinate and Y coordinate of the equivalent force. We find F sub RO by, again, this is a vector quantity. In this case, we want to make sure this is a vector, we want to make sure that we calculate those accordingly. And F sub RO, again, we express it in vectors. Perhaps it could be a little bit difficult to grasp at the beginning, but with a little practice, it should be just fine. Then we find the location of a single equivalent resultant force by using these equations, the X coordinate and Y coordinate, M sub R sub YO divided by F sub R sub ZO again. And remember that this moment would be as a result of this force applying by a certain distance of 2.13. The same thing here. The Y component, the M sub R X is also caused by F sub R sub O, F sub R ZO. In this case, this is the 800 kilonewton minus 800 kilonewton. Since it's the forces are only in the z direction, and they all only have a k. Only k appears here as their unit vectors. It makes our calculation a whole lot easier. Okay, let's take a look at this concept quiz. There are forces acting on the pole. We can reduce that to a single force and a single moment at which point? We can, is it any point? Is it point A, B, C? Basically any point, really. We can do that using the techniques that I just described. It could be point P, it could be Q, it could be R. Well, it's going to be at any point. So any of these points is the best answer. Secondly, consider two couples acting on a body. The simplest possible equivalent system at any arbitrary point on the body will have A, B, C, D, and the correct answer is one couple moment. Okay, that's part C. Okay, let's take a look at a more complicated problem in our group problem solving. It is more complicated. It's just the way the problem is. We're going to do that. There are actually two of them. This is one of the problems, and there would be a next problem, and then we would wrap it up by having an attention quiz. As you know, I'm solving lots of problems for statics, many of them here, and try to make it as try to solve as many problems as possible. So let's take a look at this particular problem. This is a 2D force and couple system as shown, and we would like to find the equivalent resultant force and couple moment acting at A. As you can see, there's a 26 kilonewton and a 30 kilonewton, and the angles are, for one of them, it's shown by the angle itself, and the other one is the triangle, the ratio of 5, 12, 13 triangle that's shown. The width of the center line of the beam itself is a distance 0.3 meter away, and that's also shown here. There are two supports here. One is acting right here, and the other one is the support that's acting right here. So our plan is to sum all the x and y components of the two forces and to find F sub RA. Then we would find and sum all the moments resulting from moving each force to A and add them to the 14 kilonewton meter free moment to find the resultant M sub RA. So let's get to it. We would sum all the forces, the components of the forces. We, again, don't set it to zero. We just sum it up at this stage. So we don't apply any of the equilibrium equations yet. So this is a summation of F sub x. Then there's summation of force sub y. And then we would like to find the magnitude and direction of the resultant force. We just use the square root of some of the squares, and that would give us 50.2 kilonewton. The tangent is also calculated similarly to the previous problem. The M sub RA, again, the positive direction is counterclockwise in this case. We are going to take care of that, and the result will be minus 239 kilonewton meter. Note that when I consider M sub RA, some components of this force, whether it's x or y, may or may not cause any moment about A. In this case, all four of them, they did contribute to the moment. And again, if the moment is cause a clockwise rotation, in this case, or it gives us the feeling of a clockwise rotation as a result of that force, it would be a negative number, since our sign convention is that counterclockwise is positive in this case. So 3 of the components of this turn out to be negative. So that would be minus 329 kilonewton meter as such. So then there's the second problem. Again, this particular problem, we are given forces F1 and F2 that are applied to the pipe, and equivalent resultant force and couple moments at point O is what we would like to determine. First, we are going to take the summation of forces. We call it sums of Fi, since this is in it's in a vector form. Then M sub Ro, we take the summation of moment about C plus summation of R sub I times Fy, F sub I, where M sub C is the free couple moments that we just discussed, and then I sub R the position vectors from the point O to any point on the line of action of F sub I. So F1, F2, F sub Ro, R1, and R2 could be found as such. Then M sub Ro, which is the summation of R sub I times F sub I, position vector, it will be calculated as such. R1 times F1 plus R2 times, I mean to say cross, not times. So these are all the cross product as we've done previously. So the cross product of R sub I, F sub I, we set the matrix as such, IJK. This is for the R sub I. This is from the force, the IJ components. The same thing here. And we would take the determinant of that. The zero forces would really help us. As such, we are going to get this the determinant, and then we don't express it in terms. Note that all the I, J, and K's, they would be added together and so on, and it will be expressed M sub Ro as 80I minus 87.5 J plus 102.5 K pound foot. So let's take care of the attention quiz for this fourth system. The equivalent system at P is A, F sub RP 40 along the positive x direction. F sub R sub P is 60. Let's see if we can examine this. It must be in the along the x direction. It cannot be along the y direction. Okay, so answer C is out right away. F sub RP cannot be 0, so that's also out right away. We can pretty much end up with A or D. On further examination, we will realize that it must be 40 pounds in the x direction, so both first component of this is fine. The problem is M sub RP would turn out to be 30, so this answer is also out. So D is the correct answer in this case. So what about the second part of the attention quiz? We consider 3 couples acting on a body. Equivalent systems will be blank at different points on the body. It's going to actually will be the same even when located at different points on the body. So that would be the correct answer in this case. That brings me to the end of the lecture. Let learning continue. And if you have any questions, feel free to send them to me. Thank you.